Hello, guys. Thank you for taking your time and spending it with me today. Um, I wanted to introduce a system design um, for everyone. It's meant for people that have some background in technology. It's probably not meant for people that have extensive system design experience, some really highly experienced software engineers. But it's meant for people that are project managers, TPMs, even software engineers who don't deal with a lot of system design questions in their everyday work. It's really helpful for people going through the interview process. It's really great for someone who wants to understand the detail, kind of a technical details, fundamentals mostly. I would say kind of building blocks of how to design a system. And by that I mean our Instagram, Twitter, those web architectures that we see and interact with every day. So with that, let's get started and dive into system design. What is a system? I think that's a that's a good question to ask. And a lot of times when we prepare for an interview or we deal with the questions of system design, it seems really scary. Wow, this is so complicated, and how do I deal with all these components and interfaces? A really helpful way to think about it, and actually this is something that helped me quite a bit, was when you talk about system, when you talk about services, web architecture, even something as complex as Instagram or Facebook, at its really fundamental level, it's really all about uploading some data from your client, whether it's a mobile phone or your laptop. You're uploading some data. This data is stored, and you're retrieving this data at some point. So if you have Instagram and you're uploading some photos, these photos are stored, and then you're downloading these photos when you want to view them at in the future. So there's a lot of complexity involved in scaling and redundancy and a lot of different features and capabilities. But at its fundamental level, it's really fairly basic, and I think we need to understand that to start, and then we can build on more details and complexity. But this is kind of a good foundational starting point. When we talk about systems, we're really talking about different tiers and complexity. You can have a one-tier system. You could just have a one computer that's running some service, and you are a client. It's acting both as a client and a service. Maybe you're just playing a video game or installed some kind of an application, and it's just one system. It's a single tier. It's both a client and a server, and is doing performing some function. Typically, when we talk about system in the context of service design or system design, we're talking about multiple tiers. There's likely going to be a client. There's likely going to be a server, a web server of some sort, for example. There's going to be a backend, some kind of a database, some kind of a object storage where we're storing data. So when you interact with this server from the client, the server contains some business logic. It will process your request. It will retrieve some data from the backend, and it will send that data back to you, to your client. So that's more typical. This, what we just described, is kind of a three-tier architecture. And what that means is, again, we have a client that is a presentation tier, which means it will obtain the information or send the information and will change its format depending on the protocol, and send this data to a server, which is a logic tier or contains the business logic to process the information, to process the request, to then forward that request to the database, retrieve some data or make some changes or upload the data, and then send the request or send the response, I should say, or data back to the client, which will then interpret it and then will present it in a format that's applicable. So very typical scenario here. And the client would be maybe a browser that you're running on your mobile device, connecting to a web server. The web server connects to a SQL database of some sort, gets the data that you're looking for, and that's kind of completing a transaction. Pretty simple at this point. However, when we're dealing with large-scale services, we talked about Instagram, we talked about Twitter a little bit. We're dealing with more than just 3 tiers. These are services that are serving millions of users, and you're going to need some additional tiers to make all of this capability happen at such a large scale. That typically involves things like caching tier to provide ability to retrieve information very quickly. Load balancing, because you're going to have multiple servers at the web or database tiers, and you need to be able to send traffic across these multiple servers. So your load balancing is going to be a requirement. Messaging queues. So when you send a message, you don't want that communication to be coupled between a server and a client. You just want to be able to send a message to a queue, and then at some point it will be retrieved in an order that's appropriate. It also allows you to kind of scale things independently. So this decoupling is going to be a really important concept to understand, and we're going to talk about it a little bit later. But messaging queues allow us to create that decoupling and kind of create this microservice scenarios that we'll see in a little bit. And we spoke about this just a little bit earlier. The web architecture, the web services. Most of the services that we can think of that are internet based are in fact web architecture type services. And an important part that we need to be aware of is the API that needs to be designed at the service tier that allows the client to communicate with the server, that allows us to have a standardized kind of deterministic way to send commands, to get the data, to post the data, to delete, to change. So it allows that interface, RPC endpoint or an API that we can interact with our service through a kind of a standardized mechanism. And the data that we retrieve is also standardized in a format that our browser is able to understand. So typically you'll see something like JSON or XML. So those are kind of a very well understood and standardized operations. REST API is the most common and widely used type of an API in web services, web architectures. In this illustration, you kind of see that there's a method, get, so we're getting some data. There's a path that indicates where this data is located. There's a protocol, HTTP, and as you can see there in the response, we're seeing it's an HTTP response. There's a response body and a JSON protocol, and there's a standard status code. So it's a HTTP transaction. And again, a great example of what REST API does. When we're discussing HTTP protocol and communication between a server and a client and a server, there's a couple of general ways that we can have this communication take place. One is through a pull request, pull method. And this is what most of us will think of a kind of a typical client to server interaction, where the client sends a request, the server sends a response, the client sends a request, the server sends a response. It's like this back-to-back, one-to-one communication between those two parties, the client and the server. In the case of a push method, it's a little bit different. It's what we refer to as long polling requests, WebSockets. If anyone is familiar with the kind of computer science concept of WebSockets, where you have this two-way communication, long-lived, long polling connection. So an example of that would be something like Netflix, for instance, where you establish a connection to a server and it sends data periodically back. You don't need to reestablish connection from the client every time. It actually reduces the load on the server to an extent, because it doesn't have to respond to this many connection requests. There is some things to think about, because a server can maintain a limited number of connections. So we need to think about how many connections can a server actually maintain, and how many servers do we need if we have this number of connections. So something to keep in mind also. And this is a very typical illustration of that. So you have client and a server, there's a request and there's a response, and then we have a request and response kind of back and forth keeps happening here. While in the case of push, it's a little bit different, where you have a single request that comes in, the connection gets established, and we get updates from the server periodically. So it's different. So when we talk about a system design, we're going to look at, does this require long polling connection or not? And you'll find that in many cases it does. So just something to be aware of as we design a more complex system. As we talked about, when the services become large, when we're serving thousands and millions of users, scalability is a requirement. Initially, when you have one or two users, or maybe even 100 users, a single server will be just fine. You can have a server in your living room and in your kitchen or in your house that runs an Apache web server. You can have some content there. You can create a DNS server for your domain. And when the users log into your web server, you'll serve some content, and your server can handle hundreds and hundreds of users concurrently. But then at some point you will scale to the point where you have thousands of users connecting to your server every second, and then you'll find that you're not going to be able to serve these users, and you're dropping their connection requests, and you're experiencing a lot of service degradation and latency, and you're going to have a lot of difficulties with your users. So we have to scale. And you might say, well, that's so easy. I'll just buy another server, and I'll buy another server, or I'll just buy a bunch of CPU and memory, or buy a bigger machine. That has some trade-offs. You might ask yourself, well, how big of a server can I build? I mean, how many? If my server today, I don't know, depending on its configuration, might serve, let's say, 100 users or 200 users. Well, if I have 10,000 users, how much more can I scale this one individual server? How many more servers should I buy? So you have to ask yourself these questions. And then when your users are requesting some content, you have to then shard your data, because it's not going to likely fit on a single server. So how do we know which server to go to? What about the latency between trying to send data between the servers, depending on where they're located geographically? So some things that we need to think about. There's trade-offs between having a single machine that's very, very simple to maintain. I just need to worry about this one machine versus 100 machines, or multiple machines that you need to think about maintaining, replicating data across, and think about different scenarios that could go wrong. So you have a lot more to think about when you have multiple machines, but yet there's also a lot of advantages. Um, some of these advantages we talked about, but there's one in particular that's really worth mentioning. When we talk about vertical scaling and horizontal scaling, vertical scaling is you just make that single server more powerful by adding memory, CPU, disk, etc. Horizontal scaling, you have more inexpensive hardware. Some people refer to it as commodity hardware, but you have a lot of instances of that hardware deployed on your in your network or in your domain. So the advantage of horizontal scaling, besides the fact that you have much larger capacity, server capacity, the advantage is that you no longer have a single point of failure. If you have a single service that fails, your service becomes unavailable until you fix it, and so you have essentially affecting you impacted your service availability while you're fixing your hardware or whatever the reason was for the server to go down. In a horizontal scaling case, if the server goes down, it's totally fine because you have other servers that will be able to serve that traffic provided you have correct replication mechanism in place. But that essentially is one of the reasons why horizontal scaling is so prevalent in all of the large uh, services that we are familiar with. Another thing to think about when we talk about horizontal scaling or having multiple machines serving our traffic is the fact that we need those servers to be stateless. What does it mean? Let's think of an example. Let's say you're purchasing something on an e-commerce store and you entered your credit card information, your name, your address, and everything else, and then that server that you're interacting with, let's say it failed, or let's say something prevented your connection from from persisting. So the connection went down. So now you reestablish your connection with a different server, and what happens is that all of that information is lost because it was associated with that server that is no longer available. So we're in a pretty bad state here because then you have user that has to re-enter this data. It just becomes really a bad user experience, and there's a lot of other problems that we need to deal with then. Um, when we make that state metadata um, external from the server, when we decouple it and you have this additional storage, shared storage layer or tier, then we don't have that dependency. And when you connect to a new server, that's not a problem because it will just be able to access that metadata from this shared storage. And as a user, you won't be really noticing a lot of disruption as a result of that other server going down or your original connection being disrupted. So it's an important concept that we need to understand, being stateless when we talk about horizontal scaling in multiple servers that are serving traffic. All of these servers are likely connected in a cluster. It's a collection of servers. They're all performing the same function. They all share their state through some kind of a heartbeat or some kind of protocol that allows them to be aware of each other's state. It's important for replication when you have, let's say, three-way replication and your service is aware that two of the instances are down, for example, and let's select another server to be part of that three-way replication. So it's just coordination that needs to happen there. Zookeeper is a kind of service that performs that coordination, but it's something that we need to be aware of when we talk about a cluster or a collection of servers. And this illustration kind of shows that we have the communication between the servers there's a virtual address, and we talked about load balancing a little bit. So there's a virtual address, and there's these servers that probably have um, maybe on the same private IP address network, but they're all connected to each other, and there's this awareness. And when your connection from the outside, from the internet, from your client comes in, um, it will hit the load balancer on its virtual address, public IP address, and then it will push the traffic to some server in the cluster. So you have high availability in this scenario. And this is kind of a typical case when we have horizontal scaling of our service with multiple servers at each tier. Which is a good segue into load balancing. We talked a little bit about load balancing. When the traffic comes in from the internet, it can be sent to multiple servers, a pool of servers, because as we talked about, we horizontally scale our service. So we have multiple web services, let's say in this case, multiple web servers. And the load balancer performs this function. It sends traffic to one of the available servers. It may make the decision based on just a round robin method, where just pick a server that's available, and the next connection comes in, you pick some other random server. So you kind of have this evenly distributed connections throughout the servers in the pool. There's other mechanisms that load balancers can be configured to use for load balancing. We can also perform some kind of keep alives or health checking to make sure that we can pick the server that has the least number of connections, or we can avoid servers that are not answering or in a particular port. So we can do a lot of these health checking to make a decision about which server is alive or which server is most available, preferred. So load balancers can do all of that complex functionality. They can also take on processing of SSL, terminating SSL connections. So that will take that load off of the server. So there's a lot of important functions that load balancers can perform. One thing I wanted to emphasize is that when I talk to some of the folks that are new to system design or system architecture, a lot of them say, well, I put my load balancer right in front of my web server. And that's a good decision. But one thing to keep in mind is that you can actually put load balancer anywhere where you have a collection of servers. You can put load balancer in front of your caching servers. You can put it in front of your database servers. You can put it in front of any part of your design where you have a cluster of servers that perform a certain function. So load balancer can distribute traffic amongst these servers. Something to keep in mind as you draw the diagram of your system. And we talked about this a little bit, a different mechanism for load balancing. There's wait round robin, where we can prefer certain servers. We can look at the number of connections and prefer the ones with the least number of connections. We can look at the response time and send direct traffic to the server that has the least response time. We can do hashing based on a source and destination IP address, and that scenario we talked about with Amazon when you, or any kind of e-commerce, when you're making some purchases. So for instance, you want to prefer your next connection to go to that same server. So we want to make that decision based on the source and destination IP address to keep the connections consistent, which is good for performance, obviously. So something to keep in mind. There's also DNS load balancing, something to maybe briefly mention. You can have a domain name with multiple A records or CNAME records, and so this one request to a particular domain can be sent to multiple IP addresses, which is kind of load balancing. It's probably not ideal because for a couple of reasons. Is you have very little control over which of the servers will be receiving traffic, because DNS resolution is pretty random unless you really try not try to add some configuration, but it's for the most part going to be random. Another thing is a lot of times the client will cache a certain DNS resolution. So if you have a server that goes down, or you want to make some changes, or you have server that's going through maintenance or RMA, that client might still be sending requests to that same IP address because they have their DNS resolution cached for some amount of time. So it reduces the flexibility for us. So we typically want to limit that as a primary way of load balancing. A few words about hashing, consistent hashing in this case, and this concept is really relevant for sharding data. And we talked about having multiple servers and having data distributed amongst these servers. And we have data sharded across a number of servers, and we have to make a decision. A service has to make a decision. Okay, I'm looking for this piece of data. Which server hosts this data? How do I know? It's an interesting question, and we can solve it in lots of different ways. But let's talk about the simple way here. Let's say we're talking about images. So maybe we're doing something similar to Instagram, and we have a bunch of images that users upload and download every second. Your image would have an ID. So if you think about a database table, image ID would perhaps be your primary key. And so we can hash this key, and we perform a modular operation on it. And that, let's say we have 10 servers, we do hashing modular 10 operation, and it will decide based on that output which server hosts that data. That sounds pretty doable. But then you ask yourself a question: what happens if one of the servers goes down? So instead of a set of 10 servers, now we have 9. What if we have to add another server? Now we have 11 servers. So what happens? This modular operation has to be performed again. We have to re-shard this entire data set as a result of that. That's not ideal scenario, because servers can go down all the time, especially if you have hundreds and thousands of these servers. The hard drives fail, and the servers fail literally every single minute. Now, how do we deal with that scenario? Consistent hashing deal with it by building a kind of a conceptual loop. And so the servers are placed around this circle. So let's say you have an IP address, for instance, on each of these servers, and we're hashing this IP address or host name, and that's how we locate the server on this circle. For simplicity's sake, let's say it's a 360 degree. It's a circle. So let's say our hashing operation returns some number between 0 and 360, and that will determine where the server is located. And the same thing for our data object. We'll perform some kind of hashing operation which will determine where on the circle, on this conceptual circle, this object will be. And then we decide whether or not we want to locate our data in a circle, in a clockwise or counterclockwise direction. So in this example, it's a clockwise direction. And so if you have an object stored at this particular point in a circle, we can ask, okay, which server should it be on? Well, if we go in clockwise, it's going to be on this server. And same thing here for these two objects. They're going to be on this server. Again, we're going clockwise. And here's an interesting difference. If, let's say, this server here goes offline, it fails, goes for RMA, maintenance, whatever. What happens with this object here? Well, what happens, it simply goes to the server right next to it, right here. There's no need to recalculate and rehash, reshard the entire data set, just the server that's closest to the one that was removed or added. Makes things a lot easier. And so keep that consistent hashing in mind because it's a really important concept to understand. Briefly talking about the microservice architecture. We touched on it a little bit when we talked about messaging queues, but it's an important concept to understand in a general sense. Whenever we have any kind of functionality, let's say we have service that downloads some data and also uploads the data, we really want to split those two operations as much as we can to create a very specialized service. Even we talked about generating IDs for our images. That should probably be a separate service. You might ask yourself, why should we do that? Why can my web server perform all of these functions? Why can't it just download, upload, and create IDs and generate news feeds and everything else? Well, you can do that, but it's not ideal. And it's not ideal for a couple of reasons. One, you want to remove the dependency on these functions. So if you have a server that's doing all of these things, whether it's uploading, downloading, generating user IDs, generating image IDs, breaking your data into blocks, compressing and replicating, all of these things, it's just one server that's doing it. What happens if you lose that server? You lose all of that functionality, and now you have to trying to fix this problem is going to be much more difficult. Also, in our example of uploading, downloading, do I want to scale both of these at the same time, at the same rate? Probably not. If my service is really read heavy, or I'm mostly downloading data, I'm doing very little uploading in comparison. Like, if we talk about Instagram, for instance, most people viewing images all day long, they're uploading very infrequently in comparison. So it's going to be a really read-heavy type of service. So these microservices that's responsible for downloading data may need to be scaled more than the microservice that's responsible for uploading data. So we want to keep those as separate as possible for that reason. Another reason is the development. You want to keep a separate code base for each of these services. If you have to release a new feature, or you have to do some kind of optimization or refactoring on a particular part of your service's functionality, you want it to be really separate. You don't want to have this monolithic code base where each change requires changing everything. When we talk about integration testing, it becomes a nightmare because this one change can impact your entire service. You want to isolate the impact of your changes as much as you can. So there's a lot of reasons why microservice architecture is so important, especially when you scale to very large services. Let's talk about databases. Databases are obviously essential for any service. Without a database, we probably don't even have a service, unless it's something really, really simple. But anyways, there's different types of databases. There are relational databases that are kind of SQL databases that have a very strict schema, that are really good for type of transactions that have to be really consistent and very well controlled. You have this very specific structure, so when you perform very complex operations like these complex joins, it becomes really easy because your data is organized in a very structured way. The query language is also very structured, so it makes these type of transactions much, much simpler. It also has these really important qualities that we refer as atomicity, consistency, isolation, and durability. Atomicity means that we have operations that involve multiple steps, but they should all be completed entirely as one set, and fail either fail together or succeed together. I'll give you an example. Let's say financial transaction. You're transferring money from one account to the next. The successful transaction means that the money was subtracted from account A and added to account B. If the money was subtracted from account A but never added to account B, that is not a successful transaction. That's a failed transaction. So that's what atomicity is. Consistency means that the transaction was fully consistent. So we talk about multiple servers for our service. Let's say, for instance, I uploaded some image to server A that's located in California. To a client that's located in China, that transaction wasn't successful because they didn't see my image. So that's not a consistent transaction. If we talk about kind of financial type of application, if I am in traveling in New York and I uploaded some funds to my account, in Wells Fargo in California should be able to see that transaction. They should be able to say, okay, that transaction completed. That's a consistent transaction. If it's not consistent, they might say, well, I don't see that transaction you just did. It's like, well, no, I got success. The money was deposited. Well, no, we don't see that. So that's not a consistent transaction. So it's very important for these types of applications like financial transactions to be very consistent. So if you're talking about even kind of health transactions, so if you uploading some medical records and, well, we didn't see that record wasn't consistent, and then you getting a prescription for some medication and that prescription could be completely wrong because the transaction wasn't consistent between the two medical institutions. So the consistency is really important in this case. And isolation is kind of related to that to an extent. Isolation means that we want to isolate the transactions. So for instance, if I'm transferring money, you want to isolate those transactions, meaning that when money was subtracted from account A, I don't want to say, oh, success, transaction completed. I want to kind of isolate that transaction and don't show the transaction was successful until it's fully completed. So it's kind of isolating individual transactions, even though it's done at the same time, like I'm moving money from one account to another. I want to treat those transactions as though they were serial, to kind of isolate transactions. Durability, it means that once the transaction is done, it's fully completed. Meaning, if the server is to go down, or if its memory were to fail, this transaction is there. Once I receive success, I know the transaction completed. The transaction will persist. So that's kind of what that means. So this kind of a SQL databases have these properties. And they're really important when you talk about really complex operations that require very strict schema, or transactions that require this very strict set of controls, like financial transactions was an example we talked about. Now, NoSQL databases are completely different, or somewhat different, I should say. NoSQL databases, they don't have a strict schema. They're meant to work really well for horizontally scaled type of systems. They don't often have strong consistency, and Instagram is probably going to be a good example here as well. So if I'm uploading some data to a server in California, uploading some image, for instance, I have a friend in New York who might not see that image for a little while because it's not fully replicated yet. Actually, that's fine. When I upload my image or my video, Instagram will say succeeded. No problem, because they're dealing with or they're choosing to have their transactions to be eventually consistent. So at some point in the future, a few minutes later, for instance, this friend in New York will be able to see my picture, but maybe not instantly. That's fine. That's a eventually consistent transaction. It's meant to store data in a kind of a key value pair format oftentimes. So it's really simple to scale. It's very fast to access, but when you require a lot of join operations, it might be difficult because then I have these lots of different tables I have to go to access this information to join together. Sometimes we overcome that by having our data being not normalized, meaning that we can have multiple instances of the same um, data in different places to enable that kind of join operations, but it's not really meant for that in most cases. So just something to keep in mind. This kind of illustration shows the fact that there's lots of different types of databases, and um, our systems oftentimes use multiple types of databases depending on the requirement. When you talk about Facebook, for instance, I'm aware that they use all kinds of different databases for different needs. Like MySQL could be used for any kind of monetary transactions or any kind of complex relationships between users and their followers, for instance. Then there's key value databases that are great for fast reads, like caching data. If you have a wide column databases that are good for running analytics on a large kind of big data sets. Um, you have each table that has hundreds and hundreds and hundreds of attributes or columns. Um, so that's great for that because you can then run analysis on this one table to get some really valuable um, data points. And then you have graph databases that are also good for um, looking at relationships. You have the edges and nodes and how do they interact together? What's the relationship between user A and then user Z? How they're connected together. So that's really good for that. And then documentation-oriented data stores, they're good for search. It's kind of think of a JSON format. Let's say you're looking at the Instagram page or LinkedIn page. You can actually look at the JSON format and you see different fields associated with, let's say, a user account. So it's really easy to use for searching. A typical use case for that. A quick illustration of what a key value database is. You have the key, you have the value. Um, Key simply means an ID. Think of it as an ID, and then the value is just some data associated with that ID. So there's let's say there's a image ID, and then there's an image reference. So there's like this key value pair. Really good for caching and instances where you need quick access to data. It's very easy to associate. And then we talked about wide column databases. As you can see, there's a table with lots and lots of columns. Each one represents a particular attribute, and it's really good for things like large data set, data analysis, and things of that nature. A great example of a document database, and as you can see, it literally looks like a document. The JSON format shows different strings and different attributes for a particular for a particular data set. So it's again really good for things like search. It's a semi-structured data, very flexible. Um, you know, some other applications could be kind of like time feeds, user comments, games where you have scores, something very flexible. And then the graph databases are, again, really good for looking at relationships. You have nodes, vertices, or entities, and their relationships, edges. So if you want to trace a relationship of one object to some other object, is really good for that. Something to keep in mind. And this is illustration of when we talked about eventual consistency. So I'll just talk about it really briefly here using this illustration. Again, let's say you some user let's say Instagram or Twitter user, and you uploaded some message or some image to this particular North American data center. There's this data center in Asia, Singapore. When you upload this data, when do you receive success response? Is it when it's first located on this server here, or is it when it's fully replicated all across? That's really what it means, the difference between the eventual consistency and hard consistency. Eventual consistency means, okay, success, you uploaded your data. And then eventually it will get replicated. And in strict or strict consistency means that you don't receive successful transaction until it's fully replicated across the entire set. So in this case, it's like a three-way replication. So until it's fully replicated across this set of three, it's not fully successful. And this is actually quite a typical setup. In a three-way replication, typically you have two servers that are kind of in the same data center, the same cluster, and then the third one will be elsewhere. So we have this whole data center, whole cluster failing, we still have some data, same data replicated elsewhere. So this is a typical scenario, actually. So again, eventual consistency means that as soon as your data is on one of the servers, and then eventually it will get replicated. And strict consistency means that it has to be replicated fully before we receive success for that transaction. CAP theorem is actually a really good segue from when we talked about eventual versus strict consistency. And this theorem basically talks about the fact that you can't have both consistency and availability. You really could have just one. When you have your data partitioned, let's say you have two servers or three servers in the previous slide, and let's say one server goes down, and then you have to have some kind of you as a user, you have a transaction. I could choose the way to deal with that transaction. If one of the three, like in our example before, if one of the three servers is down, now we have only two, do I say this transaction was successful? If I do, then I prefer availability. I want my service to be highly available, and I don't care so much about consistency. Eventual consistency is fine. Another choice is I want to say that the transaction will fail until all three servers in my three-way replication group are up. That means I prefer strict consistency over availability. When my user tries to make a transaction, it will give them an error. It's like that service is unavailable. Is it good? In some cases it is. It's a requirement when we have really strict consistency requirements. In the majority of systems that we are dealing with as a user, Facebook, Instagram, Twitter, etc., eventual consistency is just fine. We prefer availability much more so than strict consistency. It's perfectly fine for the service to be inconsistent for a little while. It's not fine to give errors to users and then they will just be frustrated and stop using our service. So again, when our service is partitioned, when we have to choose, there's no way to have both. You could have either strict consistency or availability. So that's what CAP theorem talks about, is having to make those choices. As a system designer, that's something we have to think about. We talked about caching to an extent, but this is kind of another introduction to it. What is caching? Why do we need caching? Well, the whole fundamental reason for having caching is because retrieving data from disk is very, very slow. And we would rather retrieve data from memory because it's much, much faster. And so we want to store static data in cache, data that's not frequently changing, so that the user can connect to to our service and retrieve that data a lot faster. If it's not in cache, then we would retrieve it from the database and then return it to the user and then cache it later. So that's kind of a mechanism for doing that. It's really important concept when we talk about CDN, content distribution networks. Think about YouTube and think about Netflix. You want to serve the data closest to where the user is located. So we want to serve it cached at some edge location closest to the user, and the request will go to the CDN first if it's available, if it's cached there. Let's say a YouTube video that's really popular, most likely is going to be cached, so we're going to retrieve it from cache. If there's some obscure video that nobody has ever seen or hasn't seen in a long time, most likely we'll have to go all the way to the service's core data center backbone somewhere and retrieve that data much slower, and then eventually it'll get cached. So caching is really important. Is a faster way to retrieve data. It's a great way to optimize our services performance, and we have to think about when we build our systems to make sure we have this caching tier. There's multiple ways of implementing cache, and we're going to briefly talk about these. I'm not going to spend too much time, but there's several methods we need to understand. There's a cache aside method, and cache aside method means that your caching server sits kind of on the side. And then, as you can see by these arrows here, the application is interacting with cache. So it's the application's responsibility to connect to cache and say, okay, is the data there? Oh, it's not. So, okay, I have to retrieve it from the database and then put it into cache. So it's application taking the role of doing this kind of transactions with the cache. That's kind of an important caveat for cache aside. Another important thing to talk about is the fact that the data is written directly to the database first, and then eventually it'll make it into cache. But initially, your application will check the cache before reading anything from the database, and then the application will update the database. And it's an application's responsibility to make sure those two are synchronized. So as you can see, there's a lot of load on application. Application has to be aware of a lot of that. Something to keep in mind. The read-through caching is different. Here, the cache is responsible for retrieving the data from the database. It's no longer the application's responsibility. The cache is responsible for reading and writing the data to the database. And retrieve the data, so the application is no longer in the loop for that. So that's a really important distinction. Makes the application development much easier as compared to the cache aside. It's kind of illustration of that. We have the cache here in the path, so the cache is now responsible for the database transactions, or the transactions between the cache and the database. And the write-through is kind of a similar concept to the read-through. The database is not updated directly, but through cache. So again, the cache is responsible for updating the database. The cache is consistent with the database, since the data is written to both almost at the same time. The good news is that if your cache were to fail, the data is not lost. The data is in a database, which is good, because let's say you have a scenario where the data is written to cache first and then eventually written to the database. What happens if the cache server fails? Well, we're going to lose that data. So there's always that risk. And write through, not so much, because we have the two writes synchronized with both cache and a database. But there's a downside to this, because now we have to write data in two places. So that makes writing a lot slower. So something to keep in mind, if the risk of data loss is really, really important to us, um, then this is a good choice because the cost of that is the write operations become much slower. The benefit is that we reduce the risk of data loss quite significantly. Um, so this is good for um, a read-heavy applications. The applications that write a lot of data, this will be a little bit slower just because we have to write in two places. So the reason why I'm talking about this is because when you study these different caching mechanisms, keep those things in mind. What's the advantage or disadvantage of different caching methods that are out there? What's good for applications that are heavy read or heavy write? What are some of the trade-offs? For instance, if we're writing our data to the database first, then our first attempt to read data from cache will be a cache miss, which is a hit on our performance because then we have to, every time we connect to, um, every time we trying to retrieve the data after it's been written for the first time, it'll be a cache miss. So those different strategies we need to keep in mind. But I don't want to spend too much time talking about this because I think we can, feel free to read about this in detail. But just keep that in mind. And also, during the interview process, let's say you're interviewing for a company that talks about system design interview, it's pretty unlikely, I would say, that you'll be forced to recite the definition of different caching methods. But you do need to understand the concept. There are trade-offs between the different caching methods. So the interviewer might ask you a question, what would be the type of caching that you would use here? You might not remember, okay, what is a read through, what is a write through, but you might say, okay, well, because it's a read heavy application, I really prefer for the data to be written to both cache and to the database because I want the data to be available in cache for much faster retrieval. Um, for a really a write heavy applications, I can choose to write my data to the database first for it to be eventually sent to cache, or to both may not be the best choice because then you have two writes every time you have to upload or write the data. You have to perform two writes. So if it's a really write heavy application, that may not be the best choice. So just thinking about those things is really important. Not necessarily memorizing, but just understanding. We touched on this concept a little bit earlier when we talked about messaging tier. And this is talking about that. It kind of decouples uh, the reads and writes on the client and the server side. We have a producer that publishes some data. We have a consumer that consumes that data. So if you, let's say for instance, you have some data that gets published and it's consumed by multiple clients, it's much easier from the application development side to simply say, we're going to have this data published to this queue, and then different clients or consumers can subscribe to this queue and retrieve the data um, um, without having to be tightly coupled with the producer. So it's kind of a pub sub architecture that Google implements. You have consumers that subscribe to receive messages produced by some producer or producers, and then um, they'll just be receiving these messages when they're available on the queue. So it's decoupling the producer and consumer from each other because you have this messaging queue or messaging tier in the middle that takes care of that. for both. And this is kind of a good illustration of that. You have some web servers that are publishing some data to the queue, and then you have the consumers that are subscribing to these topics and then consuming this data. And also, as we talked about earlier, it gives us an opportunity to scale these microservices independently. So if we find that our queuing tier needs to be scaled, we just add additional server capacity to it without having to worry about adding additional web servers, for instance, because we may not have to. Something to keep in mind. This microservice architecture comes into play. This is a quick introduction to data processing. I think this is a really high level concept, but it's good to understand. Let's say we have some system that produces some data, some messages. These messages could be either real-time streaming, or this could be data that's kind of batched periodically, but it's the data that constantly gets generated and it's sent to the data processing layer or tier, where this data gets processed and it is sent to some visualization, some business intelligence, some way that can be consumed by users or by machines. A good example of that, again, I'm going back to banking or financial transactions. Let's say you have a bank and then bank account, and then you travel to some other country, and then you're trying to buy something. Oftentimes, you get a phone call or a message from your bank saying, "Is it so and so that made this transaction?" Because they know you're located in California, for instance, and now you're in France. They want to verify that you are the right person who made this transaction. How do they know that this happened? It's almost instant that they'll send you that message. Sometimes they can actually block transactions from happening in real time. There is a speed layer that's streaming data that constantly gets updated. Almost not in real time, but almost in real time. But now there's also a batch layer. So maybe every 24 hours, banks go through this entire set of transactions that happened and do some analysis. How much money was received, how much money was invested, etc., etc. Those are batch operations that happen periodically. They might not happen every 24 hours. Maybe they happen every hour, but they don't happen in real time. So this kind of a topology scheme talks about that. There's different layers: speed, which is streaming real time, and batch, which is periodic. All of that data gets processed in some way and then gets sent to be visualized in a way that can be consumed. So, general concept, and we kind of can illustrate that a little bit here. We have some data gets generated. It is sent to two different layers. One is a batch, one is a speed layer, and then there's sent to the serving layer, where it can be consumed by clients or by different other services. So it kind of talks about separating the two types of data, batching and streaming. That's kind of a quick illustration of that. When we separate the two layers, we often refer to this as a lambda architecture. When we have a single speed layer, we don't have a batching layer. It's really just the streaming type of transactions that are happening. This is a kappa architecture. It's something to keep in mind. And now we came to a more interesting part of this discussion. I think now we understand a little bit about different components that make up a system. And we have some idea of how to build a system. We have different layers. We have the client, we have the servers that are clustered together. We have the load balancers and the cache to optimize the performance. We can talk about replication. We can talk about sharding data. So we have some really good ideas about messaging, queues, and how to decouple different services. So we have some fundamental idea about how to do that. But now we have to ask ourselves some questions as a designer, somebody who is designing a system. What are the requirements of my system? What is the system going to do? Those are functional requirements. Do I want my system to be able to process financial transactions? Do I want my system to be able to, for users to upload their images to some portal? What is our system doing as functional requirements? The non-functional requirements are the characteristics or attributes of the system. How many users should it support? How much data does it support? For instance, if all you can afford is, let's say, 10 virtual machines or 10 physical machines, can I store data for 5 years for a million users? Probably not. So those are non-functional requirements to think about when we're designing our system. If I want to guarantee a certain speed of transaction, so I want all my transaction to happen within 1 second, but then you don't have any money to spend on purchasing servers that have a lot of RAM, like caching. So you don't have the caching tier. It's going to be really difficult to guarantee these transactions. Or if you don't have a CDN layer, this caching layer, very difficult to guarantee this kind of speed. So thinking about our non-functional requirements is also going to be very important. If again, the scaling of our system will be dependent on these non-functional requirements. Considerations. We talked about just about all of those. Keeping the web tier stateless. The state kept in some shared memory that's not dependent, removes the dependency on a particular server. We should have redundancy. We should completely avoid single point of failure. If you have a single firewall and that firewall fails, your entire service is down. So make sure you have redundancy. If you have a load balancer and the load balancer fails, your whole service is unavailable. Make sure you have multiple load balancers. And that same concept applies to every single part of the system. We should be caching data as much as we can, because the return on investment is really phenomenal when it comes to that additional money spent on caching tier versus not having caching at all. So it's something that a high scale, large systems absolutely must have. CDN, we talked about it, hosting static content there. We need to think about sharding because we have multiple database servers and the data has to be sharded. How do we do that? We need to think about that. We talked about microservices architecture, splitting tiers and individual services separately, decoupling them as much as we can. We need to monitor our performance. If we are violating our SLOs, service level objectives, if we want the service to be available to our users within, I don't know, let's say 100 seconds. Well, I'm sorry, 100 milliseconds or 200 milliseconds, and then we have this tremendous latency, we need to be able to detect that, and we need to be able to address it. So for that, we need telemetry and monitoring. If we have a large number of requests that fail, we need to be aware of that, and we need to address that issue. We need to have monitoring, telemetry for that to happen. Whenever we send data over the network, it's going to introduce latency by default because our data travels over a greater distance. So whenever that happens, we need to think about compression. So something to keep in mind when we talk about system design during our interviews or with our coworkers or friends. We talked about push and pull method for HTTP, long-lived connections for push method, When is it appropriate? When is it applicable? We have to think about that. And we'll talk about it a little bit later too. Applications that are read heavy versus write heavy. What kind of caching solutions we're going to choose will depend on that. Database types, whether it's SQL or NoSQL, do we need ACID compliance? Really important. If it's just kind of a social media type application, it probably doesn't need a lot of these strict requirements that a financial application would have. Think about level of scalability. Do we have 100 users or do we have 100 million users? Huge difference, right? So we need to think about that. We need to think about traffic patterns. Do we have traffic that's really bursty? So for instance, if you monitor your bandwidth requirements for your service and it's like, well, we don't have a lot of data. Once in a while we'll get like, some little spike. For the most part, perhaps your requirements are very low. But then you have to think about when the spike happens. Does it happen consistently every night when people come home from work? What about holidays when you have, a large number of e-commerce transactions during Christmas season or Black Friday or what have you? We need to think about that. Maybe your service really depends on having those transactions succeed, and you have to be prepared, and your design has to be aware of that. And we talked about CDN. It's kind of a way to illustrate that. So we have the client trying to connect to the server. Instead of going all the way to the server, maybe the server is located somewhere in, I don't know, in Colorado, and you're located in California. You much rather connect to the server that's located in San Francisco, this edge server, or Los Angeles, than go all the way to Colorado, for instance. So much better to have this hosted locally cached here, especially when you talk about video or anything that's requires a lot of bandwidth. We talked about SLIs, SLOs, SLAs. Those are really service level indicators. How performant is our service? Really important question to answer, and how do we answer this question? One tip I would provide is that when you think about SLIs, how to determine my service is working well. This kind of a binary signal. Is it yes, is it working well, or is it not working well? Think about the user journey through the service. What are the user's expectations for the service to do? If you talk about Google search, the expectation that the service is almost instant. When I type something in and I click search, like I expect the results to come pretty quickly. When you talk about some database that perhaps you need to retrieve some information about, I don't know, some water quality data from 5 years ago, perhaps you don't expect it to be happening within a second or a millisecond. Perhaps it's okay for you to wait 30 seconds or even longer to get a response. So it really depends on what is the user expectation, what is the user journey. When you send an email, does user expect that email to arrive instantly? Well, maybe not. I think people will generally be fine if it takes 30 seconds for the email to arrive. So how do we measure our performance to tell you that our service is performing well or not? It's not performing well. So think about that metric, what that means. And an SLO is really calculating that metric over time. So within a period of 30 days, what is the percentage of time that our service was available? How many bad minutes does it have? The instances where it wasn't available. And again, the concept of availability really depends on the kind of service it is. So we have to think about that in the context of that specific service. And now we came to an interesting topic of an interview. Systems interviews are very, very common for a lot of different companies these days because they want to understand that you have this really good foundational concepts about what a system is, how it's built, some of the trade-offs, some of the building blocks. So if you're interviewing for companies like Twitter, Facebook, and Google and others, they will definitely have you talk about system design, and they'll go into depth depending on the kind of position you're applying for. If you're a program manager or a TPM, which I think this presentation is kind of built for folks that are in that role, more of a leadership role rather than a deeply technical role like a software engineer or system designer, um, we need to understand these concepts very well. We may not need to know um, deep dive details into how replication in a particular database works. The HBase will have different replication than some other database. We don't necessarily need to know those intricate details. Is it master or masterless replication? What happens if you have two masters, etc. Um, you know, that's probably not going to be important, but it's really important to understand that replication is critical. And what happens when replication fails? How does it sort of play out in terms of being consistent, strictly consistent versus eventual consistency? What is our requirements? Having that understanding is very important. How do things fit together in our design is really important. And having to ask the right questions. Things like um, SQL or no SQL. What kind of what do we need to do to eliminate single point of failures and things of that nature? So we talk about the system design. Let's talk about end-to-end system. Think about the entire functionality, the kind of what is our user trying to do, and how do we enable that? And again, it's really about data going to the system, to the storage tier, um, back to the user, the business logic in the middle that happens. Think about very general concept first. Okay, we talk about this Uber. What is Uber? That's really complicated. Well, yes, it is, but at the same time, it's still data being sent back and forth. So let's break it down into its really fundamental components first and talk about it, and then we'll start discussing the details. Um, Generally, let's focus on general concepts. We want to show our interviewer that we understand the fundamental building blocks of a system, and then we're also able to talk about some trade-offs and understand what that means. Um, in in designing a system, the user is going to be the most important. We're building a system for the users. We need to understand what their desires and expectations are, what kind of functional requirements we have. How do we work with that? Now, scaling is also really important. We are reading and writing data, as we said. Um, we have 1,000 users versus million users, the scaling requirements will be different. The type of data that's being sent, the scaling requirements are going to be different. If we're sending video, that will require a lot more storage than, let's say, Twitter, which is, for the most part, will be text. Well, maybe not anymore, but you get the point. The type of data that gets stored will play a big part in how much storage we need, our bandwidth requirements, etc. So keep that in mind. Performance expectations, like we talked about, the cost. Do we have, $200 million to spend? For Google, spending $1 billion to build a CDN edge network is not a big deal. For a company that's fairly small, perhaps it is a big deal. So maybe we think about public cloud providers like Amazon, and maybe that could be an option. So kind of keeping that in mind is really important, and be ready to talk about that. Approaching system design and kind of steps, I think, is really good. When we first talk to our interviewer and they say, okay, I want you to build this messaging system that people can post messages, and then it's available to the entire company all over the world. so that employees can communicate with each other. Okay, great. What does it actually mean? You have to ask those clarifying questions. Because if you jump into, okay, well, let me build the servers, I think it tells the interviewer that you are not really listening. You're not really hearing what the user is trying to do. Think of it from, if you're the owner of that business, wouldn't you want to ask those questions? Because ultimately you're trying to build something that the customer will want to use and has a lot of um, kind of usefulness to the user, has a lot of utility to the user. So what we should ask those questions. Things like, can you tell me the approximate number of users that expect to use the system? Will they be able to send multimedia like videos and images? How quickly will they need to access this data? So we're going to ask some functional, non-functional requirements questions. Once we understand the requirements, so that's the first thing, we need to really understand the requirements. But once we do, let's think about a high-level design. Something like a one-pager that you would write. Of course, in an interview, you're not going to write a one-pager document, but you still need to have this high-level design. Okay, well, this is our client. This is our caching tier. This is our load balancer. This is going to be our web servers. This is going to be our storage tier. Do we want to separate those object storage from separate object storage from metadata storage? Do we want to separate upload and download? Have it a separate microservice? Perhaps, but it would be like a really general design at this point. Then we have to do some estimating. Fairly rough back of an envelope. Okay, how many users do we have? How many transactions do they perform every day? How big is each transaction? Let's add it up, multiply, and determine how much data do we need to how much data do we need to store? How much data transfer in our network every second? What are our bandwidth requirements? What are caching requirements? So if you look at, we want to cache data, that's 24 hours old. Let's look at our data requirements for 24 hours and let's figure out what percentage of that will be cached, and it will give us that indication. So it's really important to ask the questions. It's really important to have a general design. Build what does an API look like? What kind of data will the user be sending? If it's a Twitter, they're sending a Twitter message. So we'll have the message ID, we'll have the username, we'll have different parameters in this API request, RPC endpoint. So we need to think about what that request will look like depending on our service. Here we go. This is exactly what we talked about just a moment ago, about clarifying both functional requirements, what is our system going to do, and the non-functional requirements, things like the format of the data, the structure, the different attributes of our service, how fast will it be, how much data it needs, etc. Non-functional requirements. So we need to clarify both. The more clarification you do, the better. Your interviewer really expects you to ask a lot of questions. And this is kind of an example of what back of envelope quick little calculation will look like. In this case, we have a lot of users. We have 500 million users. That's the total of the users that we have on the system. Now, only 50% of those here is our daily active users that interact with our system on a daily basis. So it's important to keep the distinction in mind. So let's think about these daily active users when we talk about calculating requirements. So in this case, each user sends 2 messages per day. So we can multiply this number of messages, and we can see that these are the messages that our system will need to process every 24 hours. We can do some some division and figure out how many messages we have per second. Then we can assume how big is each message. And we can figure out how much data we need for um, each upload and download. And we can determine our bandwidth requirements. And then by multiplying, we can figure out our storage requirements per year in 5 years. You can look through these numbers, but the important point to realize is that these calculations do not have to be precise. You don't need to spend a lot of time on mathematics, but you need to have a general understanding and discuss with your interviewer saying, okay, this is going to be read-heavy application. We have 1 million users, so I would multiply this number of users by how many messages they send every day, which will give us the daily storage requirement. We can multiply that by 365 and give us a yearly storage requirement. We can divide it by 3600 or by 24 and then by 3600 to give us per second bandwidth requirements. So we can do all of these calculations, but don't spend too much time on it, as long as you understand what that means. This is what we talked about API. So when we talk about our system, what would the message look like to the system? If I'm sending a tweet, what should be in that tweet? There should be user ID. There should be the data that I'm sending, of course. Maybe there's going to be a location. Definitely a timestamp, because we can use the timestamp to track our performance. We can also use it to generate our IDs. So again, as you're talking to the interviewer, you can talk about that. This is what we need, and this is why we need it. When somebody sends a tweet, we need to know who sent the tweet. So let's determine the user ID. Obviously the content, so we're going to have some data there. Timestamp, is it important? Why? Well, we can talk about why that's important, why it should be there. So quick, really, you don't need to go into a lot of detail, but just think about what should that message contain. Doesn't have to be everything, but just general detail is good. And high-level design. Exactly what we talked about. We have a client here on the internet, connects to the load balancer, connects to the application tier, the web servers, business logic that connects to the database and to the storage tier that actually contains these data, images or video, whatever the case may be. As you can see, those are separated. This will contain all the metadata. And this will contain just the storage objects. And then we're going to talk about perhaps some details. How do we partition the data? Important questions. Your interviewer might say, okay, well, you partition the data by user ID, right? You say, okay, yes. Okay, so all the user data will go to server A, and then another user data will go to server B, right? You say, okay, yes. Okay, great. How about the followers of that user? So the user followers table will go to server B, right? I say, okay, yes, correct. Okay, great. So all the messages to the user associated with that user will be going to that server. You might say, yes. Okay, what if that user is Justin Bieber? What if that user is a really popular person with hundreds of millions of followers? That's going to be really difficult. So some trade-offs. Perhaps we're going to store that popular user's data in a separate shard. Or we can use a different primary key to shard data. Maybe we just use a message ID, and then based on, every new message can be sharded independently of the user, because the user table is going to be a separate shard. So in other words, we can talk about all of those things. Let's dive into an example. Tiny URL service. How do we design a tiny URL service? What is a tiny URL service? What are its functional requirements? Its functional requirements is that it takes a URL, a long URL, from the user and returns a short URL. So when you paste something um, in your browser, you don't have to type in this huge long URL. You can just type a much shorter URL that will direct you to the actual domain name. So that's kind of the functional requirement. Um, it's an alias that you'll get. Um, instead of having an original URL, you would use that alias, and the tiny URL service will direct you to the actual domain name. So this is a discussion of our resource requirements. How many users do we have here? That will determine how many um, queries per second we have. If we have, in this case, we have 10 million URL shortening created each 30 days, and then we're assuming that the 101 read to write ratio. So if we're multiplying that, so 10 million times 100, we have 1 billion redirects happening per month. So months is 30 days in this case. So we're multiplying, we're taking 1 billion queries or requests, dividing that by 30 days times 24 hours times 60 minutes times 60 seconds, and it gives us how many URL shortenings do we have per second. Then we assume that each URL shortening is 500 bytes, so we multiply 390 by that number will give us the amount of traffic or bandwidth per second. So that will determine our bandwidth requirements. And then the capacity is we look at the number of messages or URL shortening requests. We times it by 12. Because we have 12 months times 5 years, and it will give us the 5-year storage requirement for our service. And so here we make an assumption that each one is 500 bytes. So we multiply our 3 billion objects per 5-year period, and it will give us 1.5 terabytes in this case as our 5-year storage requirement. So that gives you an idea how to calculate that. And then again, this is kind of an important concept. When we talk about caching, we typically want to store 20% of our data that's most frequently accessed. So if you look at the entire storage requirement for 24 hours, take 20% of that and it will give us our caching requirement. So easy thing to remember, 80-20. So here we're going to talk about API. What should our API contain? So we're posting, in this example, we're sending a short URL to our server. It returns a long URL, and then the client can use the long URL to access the actual server where the content is stored. So it kind of shows that transaction. And then what's going to be posted when we post a long URL to get an alias. Here we have the long URL string, posting that string, and then we will retrieve the alias. It shows us what that API will contain. This one kind of a quick introduction or discussion about how will the data be stored, or one way it could be stored. So you can see there's a URL here. We're hashing the URL ID, and then that will become our primary key. That table will have the original URL, the date, the expiration date, and then the user ID. And as you can see, the user ID is actually it becomes a foreign key to another table which has a primary key of the user. So that's how we connect a particular short URL to the user who requested it. So it kind of gives you this idea of how these tables are going to be put together for a metadata server. And let's talk about basic design. How do we actually shard the data? It's you don't have to go through this discussion in great detail during the interview process typically, but it's good to keep in mind the fact that we can encode our data. In this case, it's base64 encoding. That gives us 6-character short URL that we select 6 characters because it gives us more than enough variation with 64 with base64 encoding. Essentially, it means 64 to the power of 6. So it gives us 69 billion possible combinations. So 6 bits is more than sufficient for us. This talks about the fact that when you do an MD5 hash, it gives us a 128-bit value, but we only need 6. We only need 6 bits. So when we select this 6 bits out of the 128-bit string, we need to kind of think about how that will be done. So this kind of talks about some of the options. So we choose the first 60 characters to create our alias. It's possible that we'll have some duplicates. So what's the solution? The solution is, again, guess, microservice. So we can keep creating these strings for a short URL, and we can keep it in a separate service. And then when it's needed, when the new URL request comes in, we can have this short URL available to use right away. It's already pre-built, and then when it's used, it can go to a used kind of table. When it's unused, it can be located in a different table. So again, it's a microservice concept that really plays a part here. And again, this is kind of going to be our general design. So this is the load balancer, the web servers here on this side, kind of in the middle. And then you have this key generation service that we talked about. So whenever we have a request for a short URL, we are able to query this key generation service for the new key. And then these keys are stored in this backend database here. As you can see, it's replicated, standby, and active. And then another thing you notice is there are load balancers here in front of the caching layer and in front of the database servers. Something to keep in mind. This cleanup service, the reason why it's here is because it will be retrieving the used keys. Kind of like almost like garbage collection, but I don't think we need to really worry about that too much during the interview. This kind of shows us the transaction. So there's a GET request, and then we return a lone URL. So in this case, when the user wants to access the website associated with this short URL, it goes to our tiny URL service, and the user will get a response with a lone URL, which will be able to go to the website associated with that domain. This is kind of an Instagram system design. Let's go through the steps. Functional requirements. What is Instagram doing? I think everybody kind of knows that. We're uploading a bunch of photos, we're downloading a bunch of photos, we're doing some searches. We need to be able to follow some users. We need to get the news feed of all those wonderful photos that everybody posts. Pretty clear. The non-functional requirements are also fairly clear. It has to be highly available. Whenever I go to Instagram, I want this content to be available to me. When I upload a picture, I want it to be instant. I don't want to worry about strict consistency. I want it to be happening pretty quick. I want it to be highly reliable. When I upload a photo, if I go there tomorrow or the next day or the next week and I see that my photo is gone, as a user, I'll be pretty disappointed. So reliability has to be a big part of this. So replication is really, really important. You want to be able to provide that assurance to the users at all times. Highly important. In fact, I can't think of any service where the reliability is not important at all. I guess the only kind of example that I can think of is the kind of service that you query to get the data right away and then you don't have to worry about it. Like, let's say a weather reporting service. It's like, okay, what's the weather today? It gives you an answer and then, okay, fine. But just about any service I can think of, reliability is very critical. So keep that in mind when you are doing your system design. Instagram is going to be really read heavy. There's very small amount of writing as compared to reading. The downloading of pictures or images is much more frequent than uploading of the images. It's very important for that storage to be efficient for reading, the caching to be efficient for reading. So keep that in mind. It has to be very low latency. So we need to think about caching and how that's done. This is again the back of the envelope calculations. How many daily active users do we have? If they upload one picture a day, this is how many photos do we have daily. How big is each image size? Well, we just multiply and it'll give us how much storage we need per day. We divide it by the number of seconds and it will give us our bandwidth requirements for a day. When we multiply these numbers, including the metadata that's needed, like photo ID, the user ID, the photo latitude, etc. Let's take all the metadata storage requirements and add it with the actual object storage requirements, and that will give us the entire storage requirement. So if you want to go through these numbers, they're pretty straightforward and really easy. The one tip I want to give you guys is look at the number of queries that you have, QPS. If we have a million daily active users, they're each sending 2 transactions per day. How many transactions are there per second, per year? How big is each transaction? That's pretty much all we need to know. And then we can calculate everything else from there. So I think it's pretty straightforward. I don't think we need to talk about it too much. And this shows this little illustration. I drew it really quick to show you the difference between this key value pair, this user ID, and actually this is the user. User follow. So key value pair. This is more of like a this is more of a larger table that contains the user ID as a primary key, the photo ID is a primary key, the user ID is a foreign key. So this is the user table. So when we talked about our databases, so I'm going to go back there for a second just so we can revisit that really quickly here. I think this sounds familiar, right? It's a Y-column database, HBase, which incidentally Facebook uses primarily. Cassandra, Google Bigtable, so those are really flexible and really great for this use case when we're storing a lot of data about a particular object. And so a great example of how this database table will look like here. And if you recall, we talked about microservices and how we need to divide our functionality across different services. We don't want it to be a monolith. Perfect example where we have the upload images, download images as a separate service, um, decoupled from one another. We can scale it independently. We can use it completely independently. So very important concept. And when we put it all together, we introduce another concept of redundancy, of high availability. Because as you can see, the services are replicated. There's no more single point of failure. Same thing can be said about our storage and about our metadata. As you can see, there's a backup. It's replicated. If this one were to fail, we're not losing any of our data. Same thing can be said about our image storage. It's also replicated. The three-way replication. We're not losing any of our data anytime soon, because I'm sure one of these servers is going to be located in a completely different availability zone in a completely different data center. So even if the entire data center goes down, our precious images and photos are not lost. We have nothing to worry about. The world is not going to end. This talks a little bit about the feed generation. And I think one important concept to understand is, again, the microservice nature of these services. We want to have a separate service that performs this functionality, that looks at the table, that has all of the user followers. So in this table here, so we have this user has this number of followers. And it looks at maybe the 100 most recent photos for each one of those users. It puts it in its own table for each user, and then it's already pre-generated. So whenever a user is requesting newsfeed, that request will go to the newsfeed server, and that information is already pre-built for that user. It's really an important concept to understand, as you can see. And again, there's going to be some trade-offs for users that are really popular, that have millions and millions of followers, and for users that are not popular. And it's actually a good time to revisit our subject of pull and push HTTP method. For a pull method, if you are a typical user with a couple hundred followers, let's say, like me, maybe even less. Um, every time I request some update from a server, there probably will be no update. So my response will be empty. But I'm making a request. The server has to process this request. It's really inefficient. It's much better to establish, like say I'm doing some kind of messaging, like Facebook Messenger. It's much better to establish a connection to the server that's persistent, long polling connection. And then whenever there's an update, the update will, will come in. But if you are an extremely popular person, like a celebrity of some sort, then every time you do a pull request, there'll be some updates, because there's just so much activity. So for celebrity user pulling, pooling, HTTP pool is going to be the right approach, versus a push. So we have to think about those trade-offs as well. And this is what kind of the topology will look like. We have a client. You notice the CDN is here. It's going to be performing this caching function geographically closer to the user. We have the load balancer that's sitting in front of our web servers, our business logic tier. There's a cache, the Redis. service sitting in front of our feed generation and in front of our metadata database. And essentially, this is the entire data flow of our user traffic or user journey. The client will come in and will try to access the data, their images they're trying to download from the um, content distribution network. If it's there, great. They will serve the user. If not, it will go back to the object storage and retrieve that object and give it to the client. When there's any updates, um, user changes some attribute of their image or maybe upload a new image, the metadata has to be updated. So that flow is going to go through the web server or our application server. It goes to the to be cached, going to the metadata database and get updated. So fairly simple. Um, let's take a look at one more example. This is a little bit interesting. A rate limiter. What is a rate limiter? Rate limiter is actually really important. If it weren't for the rate limiter, we would have a huge denial of service problem. Actually, we already have a denial of service problem, but the problem would be a lot bigger. It basically limits how many transactions we can have. Let's say it might say you can only upload 20 images per second, or you can only request this many connections per unit of time. So it limits what users can do on the system, and it prevents us from running out of resources. It prevents us from, like we were saying earlier, denial of service attacks. It's really important to set those boundaries on what users can do on the system, and it's really important functionality. But how do we actually do it? We already talked about what the functional requirements are. The functional requirement is that the client request comes in, the rate limiting server looks at some set of rules. Okay, this user is allowed 5 connections per second. How many connections have they already done? There's another microservice that looks at the number counter per unit of time, and it will be able to make a decision whether connection should be allowed or not. That's our high-level functional requirements. How will the connection be denied? There's using HTTP code. So there's a really simple way to do it, but we just have to understand kind of what is it that we're trying to do. And this talks about the algorithm, a little bit more into detail. What would that algorithm for making a decision look like? Let's assume we have 5 requests per second as our limit within a window. In this case, we're using this kind of a sliding window protocol. So we constantly maintain that time limit as we move through, as that window moves through time. And here we talk about kind of the method that we choose to make a decision whether or not the connection should pass or not. We look at the number of requests in a previous window. We added to the number of requests in the current window. We multiplied on the percent of the overlap between the two windows. So you can see here it's 70%. So we say in 4, 1, 2, 3, 4, that's the number of connections in the previous window. 3, the number in the new window times the overlap, 70% overlap. So there's a old window here, the new window here. So there's an overlap of 70%, this area here, 70% overlap. So we multiply it. Is it less than 5? Is it more than 5? So it's 4, so it's less than 5, the connection can go through. High-level design, fairly simple. Client connects to the rate limiter. Rate limiter looks at cache to look at the counter. that's rate limiter performing that function that we looked at earlier, but looks at the counter to get the numbers, the number of connections per each user, and makes a decision: should I forward it or not? If yes, it forwards it. If not, it sends the HTTP response back saying not allowed. Again, the HTTP response code 429 would be kind of a way for us to return to the client, or we can add the connection to the queue and process it later. So it's really up to us. We can talk about those options that we have. This is kind of a more of a detailed design. It incorporates the messaging queue that we talked about, because connections can go to the messaging queue. These are the requests that are dropped. Maybe they're queued. This is a cache storing our business rules, like how many connections are allowed, counter, and then the workers will pick up these counters and the rules that are stored, and then process each request as it comes in. So we can increase the number of workers if the number of connections is greater, so we can kind of monitor and scale as we need to. So as you can see, this diagram is pretty complete as far as what's needed for this particular service. Some additional considerations. How much resources do we need based on the traffic patterns? Is it really bursty? Do we need to scale some part of our service? Do we need to scale caching layer? Do we see any servers? Server side errors? Do we see any latency? Kind of keeping track of our metrics and making decisions based on what we're seeing. Great example, Dropbox. Dropbox is actually a really interesting service from the design perspective. So let's dive in and take a look at it a little bit more. I think the requirements are pretty well understood. We need to store some data in the cloud storage, so to speak, and which is what Dropbox is doing for us. We need to be able to retrieve this data. Now, we talked about ACID requirements. This is going to be really important when we talk about attributing a particular data. Some of the data may be really important. Some of the data may have, implications for that user. Maybe it's need to be kept secure. This transactional retrieving data, receiving data. So associating data files to a number of different clients, because each user can have multiple clients, their laptops, their mobile devices. So the transactional consistency schema is much more important here. That's why it's listed as a potential requirement. Let's look at some design considerations. We have read and write volumes are pretty much identical because a lot of users actually use it quite a bit to store their data. They don't necessarily access their files every 5 minutes, every 5 seconds, but they do upload the data periodically, and when they need to, they do retrieve the data or files, and so it's pretty equal split in the middle. When we upload these large files, we really want to break them up into chunks, and this is what we do here. We choose 400 meg as a chunk size, and we chunk up this data into bits. It can help us with reducing the bandwidth requirements, because we can only, when we retrieve the data, when we update some part of our files, we only need to update the blocks that have changed. So that's one consideration. Another thing, we can keep the metadata on the client side to help with performance and reduce some of the server load. So that's another consideration here. And this is a capacity requirements, kind of a back of the envelope calculation. We have 10 million users, for instance, in this case. Let's assume that each user has an average of 100 files. One file is 100 kilobytes. We do the multiplication that gives us the storage requirements daily, or 100 files, let's say, per day, or is it per month? So that determines our storage requirements. A bandwidth estimates is really dividing this number by the number of seconds. So this gives us a bandwidth requirements per second. Memory requirements is actually caching. Again, looking at the daily number of storage requirement and looking at the 20% of that. So that gives us the caching. Pretty simple. High-level design. Again, the user can upload files to their folders. Then the server is going to be we need servers that will be able to upload and download the data. So again, splitting this functionality, kind of a microservice architecture. We need the servers that will be able to synchronize the data between the different folders, between different clients. Because I could have a mobile device that's my client. I could have a client that's my PC at work. And I want to be able to synchronize those. So that's important functionality for this. Very critical. And for Dropbox, the reason why it's so interesting is that the client is really important here, because the client is performing actually a lot of functions. Not only does it upload and download files, it also detects changes in different folders. It can handle conflicts when there's multiple users making a change to a file at the same time or about the same time. It can also perform the function of breaking the data into chunks. This is a perfect example of a long polling connection that we talked about, because file upload is going to be a quite lengthy process depending on the size of the file. So we need to maintain that long polling connection to be able to complete that transaction without having to go back and forth. At the client design, again, really important here because the client is doing a lot of work. It should maintain internal metadata database, so it maintains synchronized. It is doing chunking, so it has the chunker functionality. It's breaking those big files into chunks. It also has a watcher component that watches any discrepancies that happen on the files within a folder, and it can then report those changes to the indexer, and the indexer is what connects to the synchronization server and notifies the synchronization server, hey, there's a change here, we need to update the metadata. That allows the synchronization to happen between different clients. Well, there we go. This is breaking this functionality down into pieces. There's what our storage will need to take into account. We need to store different chunks for our files, the files themselves. This kind of what kind of metadata do we need, right? Chunks, files, users, devices, because each user might have multiple devices. Workspaces, so each user might have different folders. So we need to keep that all connected. And file permissions, because each file can have multiple permissions. If you look at all this metadata that needs to be stored, now you begin to understand why the ACID is going to be important here. Remember we talked about SQL or NoSQL. The reason why the SQL type of database is going to be more relevant here is because we're storing a lot of very complex and very detailed metadata that needs to be kept in sync. So it gives you an idea why that design choice was made earlier in this deck. And this talks about each of these functions on the client side and the server side individually. The synchronization service it processes any file changes, and on the local client, there's a synchronization service. It synchronizes with um, the web instance of the service, or the cloud service synchronization service, and that's how we update the metadata DB whenever there's a change happening to one of the files. And again, the clients communicate with the synchronization service, um, and then get updates on any objects that change. So if you have a file that's shared with you by someone else, they update the file, there'll be notification, oh, this metadata has changed, and your client will download the chunks that have changed, so you have an updated version of that file. And this is kind of what talks about that here. When synchronization service receives an update request from a client, it checks with the remote metadata DB to make sure it's consistent, and it updates the remote metadata database. It then also sends a notification to other clients through the synchronization service. And then we can use hashing to determine what actually changed. This is a really cool illustration of the metadata. I'm sorry, not the metadata, but rather the messaging queue. A great illustration of the messaging queue, because what we're seeing here is you have multiple clients that are updating metadata DB through a synchronization service. And one thing that you notice here is there's a request queue that all the clients connect to. There's a single request queue here, but the response queue, there's one per client. So remember that, keep that in mind. The request queue is just one for all the clients, they're shared between all the clients, but the response queue is one individual per client. So again, it gives us that decoupling between the client and the server, the metadata DB in this case. So it's an important concept to illustrate here. And this is what our overall architecture will look like. We have, again, the load balancers. As you can see, there's multiple different clients. There's a mobile client, there's a laptop, there's a PC here. They're all can actually belong to a single user. But nevertheless, they all go through a load balancer, connect to the application server tier, and then we have the messaging queue as we talked about here. Remember, we have a single request queue, and we have the individual response queues for each client. There's a synchronization service, so as you can see, any metadata updates go through the synchronization service here. So remember that any updates back and forth go through synchronization server. And the synchronization server is responsible in detecting and notifying all the clients about any changes to the metadata. Whenever their files updated, it will be responsible for notifying all the clients about that. And then we have the storage server that keeps the actual files. We talked about it a little bit earlier, but it's an important concept. I want to touch on that a little bit more here, just really quick. Why do we split storage, the object storage or cloud storage, and the metadata server? Like, isn't the object already contained? Does it already contain the metadata? The reason for that is because the metadata server is specifically designed to keep the metadata, and it could be really elaborate. It could have a lot of metadata, especially when you talk about a service as complex as Dropbox, because you could, as you saw here on the slide, there's a lot of metadata that we need to keep. And so we don't want to keep all that in a storage server. We want to keep that separate. The storage really just contains a key value pair. This is a object ID, and this is the object. This is the file. And all the metadata about the server, about the users, about the clients, about different chunks, all of that is in metadata service. So we want to keep those separate, and that's why they're positioned this way in our diagram, in our system design. I hope it was useful. Thank you for listening. I hope I was able to provide kind of a general overview of what the system design is. It will help you in your job, it will help you in an interview, or just a general understanding of how systems are built, especially the large systems like we interact with every day. Thank you again for listening. And please don't hesitate to ask any questions. I will be very happy to talk to you to provide answers and happy to engage in any discussion. Have a wonderful, wonderful day. Thank you again.